Okay, so here's a visual aid for what I was talking about in the last video. So what we're going to do is we're going to show how you can use a sampling distribution to a population parameter better than just using the sample data or one specific statistic. So up here we have a generic normal distribution, right? And it's the population distribution. We can mess with it if we want, but for now, we're just going to leave it as is, right? Let's assume this is something pretty, vanilla, like average heights. That's my go-to, right? So for now, we'll keep it like a small sample size, right? So let's say we have one person who's going to pick two people at random and average their heights together. So they pick two people from the population. Oops. So they picked two people from the population and took their average height, and then they took two more people and found the standard deviation, right? So it's doing two of these at the same time, right? Another person comes along and does the exact same thing, and they get, different mean and different standard deviation. So for right now, we have four different people, and we can keep going. It's three different statistics, four and five different statistics. We can keep doing this for quite a long time, and we can keep going, but instead of doing that, I'm just going to go by fives now, right? So if I took five at a time, if I took five at a time, I see that my mean, represented by the blue line, and my standard deviation of those means, represented by the pink line, and then again we have a standard deviation down there. And every time I add a new statistic to it, it moves my mean ever so slightly. And let's just go by fives. Now we can see after not very long, this starts to take a pretty normal looking distribution. It's a little bit weird, but given enough time, it sort of mimics its parent population as well as the standard deviation does as well. This one's a little bit weirder, but if we increase our sample, how many times we're doing this, then we see that it gets a lot more normally distributed a lot faster. Now, same can't be said for the standard deviation, but it is what it is. Standard deviation looks a bit skewed. That's okay. So basically, even with a small sample size for each individual statistic, we got pretty good sampling distribution. The sampling distribution for this mimics its parent population. Now, what's going to happen when we increase the sample size to 5 for both the mean and the standard deviation? Well, we're going to take 5 different statistics, find the average of those 5, and then add that to our little dot plot. And when we do this enough times, we see, our mean is changing every time, here and here. The mean we're shooting for is 16, so right now we're underestimating it quite significantly. But let's add, let's start going by 5 at a time. Okay, again, so not too long until our sampling distribution, our distribution of the mean of our statistics, starts to match what we were going with before, or what we had before, right? And down here, this one looks a little more normal than before as well. It's still not that great, and it still takes a while for things to sort of level out, but we see that when our sample size is 5, it happens a lot sooner, right? And again, and on top of that, notice that the spread of this distribution is a lot smaller than the spread of the one before. Before, our range on this was quite significant. Now it's gotten a little bit slimmer. Now, as hopefully you can tell by the way things are going, when we increase the sample size to 25 for each, so it's taking 25 data points and it's going to find the average. That's going to represent one dot on the dot plot, and it's going to do it again, and it's going to represent one dot plot on this one. And we can do that a whole bunch of times. Notice how much skinnier this is. I don't know why this keeps going all the way in here, but notice how much skinnier, how less wide this is, right? So I'm going by fives, and again, it's a lot more normally distributed. It's a lot more normal looking, a lot sooner than the parent population. It's also a lot more precise. We have a mean that is very close to our parameter with not very many repetitions. I'm just going by fives and we're getting very close straight away. And the same is, and of course my standard deviation is getting very close as well. So my standard deviation for the mean of my standard deviation is 4.7, whereas the standard deviation is 5. The mean of my means is 15.91, whereas the parameter for that is 16. So this is doing pretty good. Now, you might be thinking, well, yeah, of course these worked because the parent population is obviously normal. So let's see what happens when it's not. Let's take something that's not normal. Let's take something that's skewed. So let's say this is like wealth distribution, right? Now, if I get a small sample size like I did before, something very small, then what's going to happen is I'm going to take a whole bunch of these samples over and over again. And I notice that this sampling distribution, just like its parent distribution, the population distribution, is skewed. And no matter how many samples I take, or how many samples I take, or how many repetitions I do of this, I'm still going to have a skewed distribution. I can increase my size by 100,000 at a time, and seemingly no matter what I do, the skew from my parent population is mimicked in my sampling distribution. I guess that's to be expected, right? However, notice that I still get a half decent estimate for the mean if I do the repetition enough times, but of course, my standard deviation is significantly off, and I'm not going to be able to do any calculations with this. So what if we again increase the sampling distribution or the sample size to 5? So instead of taking 2 at a time, we're going to take 5 at a time. And it's probably going to give us still a bit of skew, but let's see what happens. So out of the gate, we see that it's it's a little bit skewed to the right, but not very much. It's a little bit more normal looking. And after many repetitions, am I a million? So after like a million repetitions, a million simulations of this, I get a sampling distribution that is a little, significantly more normal looking than what we had before, but there is still a little bit of skew. So simply increasing the sample size from 2 to 5 from something that is skewed gave us something that is a lot more normal. Now, if I increase the sample size to say 25, which is the biggest sample size this will let me do, again, I'm taking 25 samples and taking the mean of that 25, making that point, and now I'm going to take the standard deviation of 25 samples and have a dot for that. And if I do this, let's see how long this takes. There we go. That didn't take very long at all. 36 repetitions, and I have something that is very clearly normally distributed for the mean. For the standard deviation, I'm a little bit skewed still, so let's keep going for the sake of the standard deviation. That's not bad. That's a good place to stop. So I see that here my mean for my means is 7.79, and it's supposed to be 8.08. So that's not too far off. That's a pretty good estimate. And my mean for my standard deviation is 6.05, and it's supposed to be 6.22. So that's also pretty good. It didn't take very long at all. Before we were at a million reps and it was still a little bit skewed. Now we're at less than 100, and both of these distributions are clearly normal-ish, right? So it works for something that's normally distributed. Now we see that it works for something that is clearly skewed, but maybe that was just lucky. Let's make our own, something that's like really bad, right? So I don't know what the heck this would represent, but let's assume that this is a distribution, right? So some population parameter is represented by this histogram. As you can imagine, if I keep my sample size very small, I'm going to get a distribution that is kind of all over the place. And this isn't very helpful. But when we increase our sample size to something closer to 30, even something as ridiculous looking as this begins to look approximately normal after a not very long time. We're at 225 repetitions and we got something that looks normal, whereas before it was all over the place. Doesn't take too long before we get something. Well, you look at the standard deviation, that one's very good looking already. Level this out. Just thinking about it. I'll just add 10,000. There we go. Again, something that started as ridiculous. Now we have something that is normally distributed. The mean is a very close prediction, 17.74, 17.76. The mean for my standard deviation histogram is 10.9. It's supposed to be 11.16, so that's also not too bad. And yeah, we got something that looks normal. So the whole point of this demonstration is to show you that even if you start with something that is not normally distributed at all, you can make a sampling distribution from that data and use that to predict a mean for the population or a standard deviation for a population, or whatever parameter you're looking for. Some of them work better than others. Mean and proportion and standard deviation are the three that we use. Median sometimes works. Range doesn't really work, but you get the idea. So let's say I want to find the mean for a population that I know is not going to be normally distributed. Well, if I get a random statistic, if I find the mean from a random sample, that may not be a good prediction. However, if I have a large enough sample size, say close to 30, and I take a bunch of samples of that size and then find the average of those means, or the average of the averages, if you will, then what I'll get is a distribution whose mean is going to be very close to what the population's mean is, and I can use that to use my prediction. And that's pretty useful. Basically, it's a workaround for what to do when things aren't actually normally distributed, but you want to do some statistics with them anyway. So it's very useful. Anyway, I hope this visualization was helpful.